Swayam Prabha. Digital India. Educated India.
Namaste and welcome back to the video course on watershed management. In module number 4, lecture number 14, today we will discuss hydrologic processes. So, various topics covered in today's lecture include hydrologic cycle, processes, hydrologic processes, precipitation, interception, infiltration, evaporation, transpiration, evapotranspiration and runoff. Some of the important keywords for today's lecture: hydrologic cycle, precipitation, infiltration, evapotranspiration and runoff. So, as we already discussed, say related to watershed management. So, water is one of the most important resource as far as a watershed is concerned. So, as far as a watershed or as far as any area is concerned, the main source of water is precipitation or the rainfall. So, as we have discussed earlier, when the rainfall takes place, so then various hydrologic processes will be taking place once that rainfall to say transformed into a runoff. Number of processes will be there in between, like interception, then evaporation, evapotranspiration, then say infiltration, percolation, like that. So many processes are there. So, these processes actually decides say how much will be the runoff for the given rainfall condition. So, the hydrologic information whatever we are looking for is as far as the water as a resources for the watershed planning and management. So, this hydrologically watershed we can conceptualize as we have discussed in the last lecture. So, once we do a conceptualization as far as the watershed is concerned, like the boundary of the watershed, the drainage network, the area of the watershed and various say topographical and geographic condition, then say when we consider the water as a resource, so we have to see the various hydrological aspects or hydrological processes taking place within the watershed. So, as far as the hydrology is concerned, so once precipitation taking place, so precipitation to runoff, as I mentioned already, there are number of processes like evaporation, transpiration, interception, infiltration, etc. So, now as far as watershed is concerned, when we say when we deal with the water within the watershed, so we have to mainly deal with how much will be the runoff or how much is the overland flow or how much is the channel flow and then how much is the subsurface flow components like related to infiltration and the groundwater flow components. So, all these aspects we have to quantify when we go for hydrological modeling as far as the watershed is concerned. So, as we discussed earlier, so all these processes are one way or another way of the form of hydrologic cycle. So, hydraulic cycle, as we discussed, the processes and pathways in circulation of water from land and water bodies to atmosphere and back again. So, this is what is happening within the various hydrological processes. So, hydrological cycle, so start with the rainfall, then various other processes, so that there will be a circulation of the water within the say within the earth and then the atmosphere and within the hydrosphere which we consider. So, of course, as far as the various processes are concerned, the land use effects has a considerable effect as far as the watershed is concerned. The various processes what can take place within the watershed depends upon the land use and then the topographical conditions. So, within this context, say hydrologic processes, as I mentioned, so now the rainfall is taking place, then say before the runoff is formed, evaporation taking place, then interception from the various vegetation, and then the infiltration taking place, and then finally we can see that the runoff starts, and that runoff will be joined to the drainage network or the river, and that river will be say finally joining the sea or the ocean, so flow towards the ocean. So, that is the way within the hydrologic cycle the various hydraulic processes taking place. So, everything is within the hydrosphere. So, there is a balance between the water of the earth and moisture in the atmosphere due to this hydrologic cycle. So, that is what is happening. So, of course, as far as the precipitation is concerned, there is a variation with respect to the space and time, but the say overall there will be a balance between the water of the earth and the moisture in the atmosphere. So, within the hydrologic cycle. So, now as we have seen, the most important aspect of the water as a resource, say as far as a watershed is concerned, it is the precipitation. So, precipitation can be either in the form of rainfall or it can be as in the form of snowfall. So, precipitation say we can see that say we call it as rainfall when the water droplets are having a diameter of more than 0.5 mm, and we call it as drizzle when it is less than 0.5 mm, and then say it can be either in the form of snow, that means in ice form, or sleet, or hailstone, or dew. So, various conditions can be there. So, overall we call it say everything including rainfall, snowfall, everything we together call it as precipitation. So, as I mentioned, precipitation is the main source of water as far as the watershed or as the earth is concerned. So, to say out of these so many components or so many forms, rain and snow are the most important form as far as the precipitation is concerned when we consider a watershed or the land. So, the precipitation is concerned, so precipitation happens when specific condition taking place within the atmosphere. So, the what is happening is that the water evaporates on the surface of the earth or the surface of the ocean, and then it goes to the atmosphere, and then the condensation takes place. So, you can see that there is the precipitation happens only during some specific conditions, like humid air cooled to dew points and formation of the nuclei, and then the droplets are formed to raindrops, and then finally when the raindrops form to certain size, then only the precipitation is happening. So, we can see that the operation is always taking place, but we are not getting the rainfall all the time. So, that means the certain specific condition should take place say at specified locations or within the atmosphere, so that we will be having the rainfall. So, when the rainfall happens or precipitation, as far as precipitation condition is concerned, we can see that there are four main mechanisms for cooling the air to its dew point. So, as I mentioned, the first is the formation of dew point, that is the first step as far as the precipitation condition is concerned. So, four mechanism for the formation of dew point is say like adiabatic cooling, conductive cooling, radiational cooling, and evaporative cooling. So, depending upon the condition, say how effectively or how much is happening all this for main mechanism, then the dew point formation taking place, and then finally say droplets formation and say raindrops formation happens. So, if we consider as far as the earth as a whole, then we can see that say an approximation of say for example for say 505,000 cubic kilometer of water falls as precipitation each year, and out of this 398,000 cubic kilometer happens over the oceans, and then 107,000 cubic kilometer happens over the land. So, you can see that land component is concerned, it is very small, say almost say 1/5 of, or say less than say slightly more than 1/5. So, that is what is the rainfall what is happening, or the precipitation happening over the land surface. So, globally if you consider say for example, average annual precipitation is concerned, it is about 990 millimeter, but as far as the land is concerned, it is only about 715 millimeter. So, that is the precipitation pattern as far as the earth surface, total earth, or the land is concerned, say as far as the precipitation. So, now say when we talk about the water resource quantification within a watershed, so the most important aspect is precipitation. So, we have to quantify how much is the precipitation happening within a watershed, and then how much of percentage of that precipitation is transforming to runoff. So, all these are very important as far as the water resource assessment or quantification as far as a particular area of a watershed is concerned. So, the precipitation, as we discussed, say generally happens when air masses laden with water vapor are cooled. So, this precipitation we can classify into 3 types. So, the storm precipitation into 3 types. One is called first one is called frontal storm. So, frontal storm means, say for example, say the cold air is coming in this direction and warm air is coming like this. So, that there is the mixing is as in the say between the cold front and warm front, and then the various condition takes place, and then from that the frontal storm taking place. So, that is one type of storm precipitation, and the second type is so called convective storm. So, as far as convective storm is concerned, say warm moist air rises say with respect to say both as shown in this figure, and then convection taking place, and then finally when the appropriate situation or condition take place, convective storm happens. And the last one is so called orographic storm. So, in the case of orographic storms, mainly say if there is a mountain or a hilly region say on the land surface, then moist air is coming from this side and dry air from this side, and then the various circulation taking place, and finally when the precipitation condition occurs. So, we call that kind of storm as orographic storm. So, generally we can classify the storm precipitation into 3 types: frontal storm, convective storm, and the orographic storm. Now, as far as rainfall for the particular area is concerned, we have to measure the rainfall, and then we have to analyze how is the pattern of the rainfall. So, these are all very important as far as the water resource quantification for a watershed or a particular area is concerned. So, rainfall data, we have to measure the rainfall, and then we have to assess how much is the total amount of rainfall, then what is the intensity of rainfall, and how much is the duration of the rainfall. So, these are all very important aspect as far as the water resource assessment for a particular watershed is concerned. So, generally we can describe the rainfall in terms of depth of water, in terms of millimeter, and then as far as the intensity of rainfall, generally we describe in terms of millimeter per hour. So, now as I mentioned, rainfall is concerned, we have to measure the rainfall, and then we have to quantify how much is the rainfall taking place at particular locations. Rainfall we can measure as the vertical depth of water collected on a level surface. So, generally we can measure the rainfall using say equipment called rain gauges. So, generally if you go through the hydrological literature, we can see there are 2 types of rain gauges. First one is called non-recording type rain gauge. So, here in the non-recording type rain gauge, we collect the rainfall over a known period of time. So, here we cannot directly get the intensity from the, since we are simply collecting the rainfall. So, say for example, in the meteorological department IMD, so the standard gauge is concerned, this is the standard gauge. So, there is a collector with a gunmetal rim. So, this is the collector, and then there will be a funnel like this. and then say there will be a polythene bottle where we can transfer this and find out how much is the rainfall. So then collected area can vary from 100 square centimeter to 200 square centimeter, and the polythene bottle can be of the form of 2 liter, 4 liter and 10 liters, and measurement by graduated measuring cylinder. So what we do, wherever we install this rain gauge, say particular location where no obstruction in an open area, we can install this rain gauge, and then say once in a day particular time we can measure how much is the rainfall took place, and then that gives the total quantity of the rainfall. So other type of rain gauge is called recording type rain gauge. So actually this is a slightly sophisticated rain gauge. So this directly give the rainfall intensity. So there is a mechanical system within the rain gauge, so that record on the graph paper or directly on data acquisition system. So we can get the curve of cumulative rainfall with the time. So we can plot the mass curve, time versus the rainfall intensity. So the slope of the curve gives the rainfall intensity. So there are different types of say recording type rain gauges. So like a floating type weighing bucket, then tipping bucket, then clock driven floating drum, pen fitted graph paper. So like that number of recording type of rain gauges are used. So nowadays we rarely use non-recording type rain gauges. Most of the time we use the recording type rain gauge, so that we get the total quantity of the rainfall as well as the rainfall intensity directly, so that we can have better hydrological predictions as far as the various processes are concerned. So this shows a particular type of, say like a weighing type the rain gauge. So then say some of the important terms as far as the rainfall or precipitation is concerned. First one is the rainfall intensity, second one is the duration, and the third one is the frequency. So now rainfall intensity, as I mentioned, that is the rate at which rainfall occurs. So it can be generally in millimeter per hour. And then duration is concerned, generally we prescribe in terms of say in number of hours or number of days, like that. Then another important term in the hydrology is so called return period or recurrence interval. So this shows the periods within which depth of rainfall for a given duration will be equal or exceeded once on the average. So that is the definition of the return period or recurrence interval. So if T is the return period in years, so we can put it in this form: T is equal to n plus 1 m, where n is the total number of hydrologic events, m is the rank of events arranged in descending order of magnitude. So from that we can find the frequency or the probability of occurrence of an event. In percentage we can put P is equal to 100 by T. So this is in percentage. So that indicates, say, the possibility of a return of a rainfall. So then the intensity of a storm, say that gives the return period and storm duration. So we can have charts based upon the historic data. So we can assess the historic data, say for example for 5 years, 10 years or 50 years or 100 years, and then we can identify, say particular location is concerned, particular area is concerned, how is the rainfall pattern, and then how much is the maximum intensity, average intensity, minimum intensity, then we can find average annual rainfall. So like that, say once we get the measured data from a rain gauge station, we can get various details as far as the rainfall pattern for the considered watershed. So for example, now if the probability of occurrence is 1 in 10 year storm, means that describe a rainfall event which is rare and is only likely to occur once every 10 years. So it has a 10% of likelihood for any given year. So like that, once we get the rainfall data, we can we can assimilate it and then identify the rainfall intensity, average annual rainfall, then say the rainfall duration, the rainfall frequency, etc. Then another important aspect is the average depth of rainfall over an area. So, when we go for say hydrologic modeling, so we can see that for the particular location which we consider, there may not be there may not be a rain gauge. So, in that case we may have to consider some averaging of the rainfall pattern for the given storm condition. So, say there will be large, the reason is that large differences in rainfall say within short distances. So, whenever we are going from say one location to another location, there will be huge variation as far as the quantity of rainfall and rainfall intensity is concerned. So, that is why we may have to consider the average depth of rainfall say as far as particular location is concerned. So, generally three methods we use to get this average depth of rainfall. So, first one is called arithmetic average. Say for example, a particular area is concerned, say we can identify which are the nearby say rain gauge stations, and then say to identify say particular for a particular given storm of rainfall, we can identify what will be the rainfall in that all those rain gauge stations nearby, and then we can get the arithmetic average by just simply adding all the rainfall for the given storm condition, and then we can divide by the number of stations. So, that is simple average. So, that is called a arithmetic average. Then so generally this arithmetic average, the accuracy will be very less, since we are simply taking we sum the rainfall for the given storm, and then we simply divide by the number of stations. But then there are more accurate methods like Thesian method and then isohedral method. So, in the Thesian methods, what we do say it is actually to use the area weighted averaging. So, we use the rain gauge station which are nearby. So, actually the rain gauge stations may be non-uniformly distributed at various locations. So, that is why we are considering an area weighted average. So, every gauge represents best the area immediately around the gauge. So, that is the basic principle of using this Thesian methods. So, we can construct Thesian polygon like this. So, actually their step by step method is, first we can plot the stations on a map. Like these are the station, say 5 station A, B, C, D, E. Then we can connect the adjacent stations by straight lines. So, we first connect the adjacent lines, say between each station we connect the each station by adjacent line by straight lines. Then bisect each connecting line perpendicularly. So, you can see that this blue line indicates we bisect each connecting lines by perpendicular lines. Then perpendicular lines define a polygon around each station. So, you can see that here, if this is the station A, then this is the area which we can say approximate as far as this station is concerned. So, similarly for this station. So, each station we can see here. Then say the P at a station, the rainfall at a station is applied to the polygon closest to it. So, this figure shows how we do using the Thesian method. So, the average depth of rainfall in that particular area which we want to identify will be P is equal to A1 P1 plus A2 P2 plus like that, plus AN PN divided by A, where A is the area of watershed. So, total area of the watershed. P1, P2 to Pn are rainfall depths in the polygon having areas A1, A2 to AN within the watershed. So, this is say if we do not have say large number of rain gauges for a given watershed. So, we can use the adjacent nearby rain gauge station and then identify how much is the rainfall for a given storm in that particular say rain gauge stations, and then we can use this method. And the third method is called isohedral methods. So, here actually in various stations we get the rainfall. say for the given storms, and then we record depth of rainfall at locations of different rain gauges, and then plot a contour line called isohyets. So, actually these are the lines of equal rainfall. So, that lines are called isohyets. So, this is for example 50 centimeter isohyet, then 45 centimeter isohyet, then 40 centimeter isohyet. So, we can plot the isohyet as far as that area which we consider. Then say plot a contour map of P based on the gauge readings at stations. So, now say for example, this is the 50 centimeter isohyet, this is 45 centimeter isohyet. We can identify how much is the area between this 50 to 45. So, we can compute the area between each successive contour lines, and then the average rainfall will be sigma PAI divided by sigma AI. So, sigma AI is the total area as far as the watershed which we consider. So, we can identify with this. This will be somewhat more accurate method, since we are getting this isohyets, and from that what is coming is the area we are considering. So, this formula gives the average rainfall as far as by using the isohyetal methods. So, that way we can identify how much is the rainfall for the particular station or particular location or particular watershed which we consider using either arithmetic average or Thesian polygon method or the isohyetal method. So, once we get the rainfall condition for the particular watershed, now say to identify how much will be the runoff. So, we can look into the various hydrologic processes which will be taking place within the watershed. So, as I mentioned earlier, so precipitation to runoff number of or the transformation of precipitation to runoff number of processes will be there. So, we will be considering say the important processes as far as the particular watershed is concerned, and then we can quantify how much will be the losses, say like interception losses, evaporation losses or the infiltration losses. So, then based upon that we can identify how much is the runoff which will be coming to the outlet of the watershed. So, from that we can assess how much is the water say if we are going to construct a say for example a check dam at the outlet. So, this much storage is possible with respect to the given rainfall condition. So, now when we consider the various hydrologic processes, then some of the important hydrologic processes we will now discuss, and we will try to say we will discuss the available equations, important equations as far as the quantification is concerned or the methodology is concerned. Then say we will identify how we can go to the various processes, and then finally how much will be the runoff. So, the various processes as far as hydraulic processes are concerned now we will discuss. So, now the first one is say when the rainfall takes place. So, first thing what can happen is that within the watershed, so vegetation will be there, say large or small or medium type trees will be there. So, first what happens is that the leaves and the trees themselves so catch some of the rainfall. So, interception means the part of the precipitation collects on the plants canopy, that is so called interception. So, actually this intercepted water ultimately evaporates, and then so that goes to the atmosphere, and some of those things the intercepted water may be absorbed by the plant also, but that will be very minor percentage, but most of the water will be going back to the atmosphere as evaporation from the plants. So, ultimately so this intercepted water evaporates, and then so but of course when we are looking for the quantification, so we have to see this abstraction from the precipitation, and then we have to quantify. So, the amount of interception depends. So, the various factors are there. So, like storm character, so what is the intensity of rainfall, how much is the duration, then vegetation. So, mainly how much is, whether it is thickly forested or thin vegetations like this, or grass, or what kind of canopy is there. So, accordingly the interception varies. then what is the growth stage if you are considering the crops, what is the growth stage of the crops, then season, what kind of season, whether it is dry season or winter season, or and then of course wind velocity. So, the importance of interception is depends upon whether we are going for a very accurate hydrologic modeling, then we have to consider this interception loss also. So, actually when we consider say for a long duration like annual or long time modeling is concerned, interception is important. There is a significant loss will be there in terms of interception. So, now say one of the commonly used equation here I have shown the potential storm interception we can calculate using this equation. Li is equal to S plus K into E into T. So, where Li is the volume of water intercepted, S is the interception storage, K is the ratio of surface area of intercepting leaves to horizontal projections of the area, E is the amount of water evaporated per hour during the precipitation period, and T is the time in hour. So, the assumption here is the rainfall is sufficient to satisfy this S here. And now, if you want to accounting the rainfall also, then this equation can be modified like Li is equal to S into 1 minus e to the power minus P by S plus K into E into T. So, this is one sample equation, and number of other types of equations are available in literature to quantify the interception. So, interception is a major loss or major, it is significant when we consider long term hydraulic modeling, say at least when we talk in terms of annual losses. So, interception we have to consider. Then another important say once the intercepted and then the rainfall is continuing, then other type of losses can be either surface retention or detention. So, you can see that as far as the surface is concerned, say the land surface is concerned, number of small depressions will be there, and then all these depressions has to be filled by the water before the runoff can start. So, depression storage or the surface retention, that is water retained on the ground surface in micro depressions. There can be small depressions, so then micro depressions. So, this water will either evaporate or infiltrate into the soil. So, these small holdings here you can see that either it can evaporate or it can infiltrate down to the soil. Then the nature of depressions as well as their size is largely a function of the original land form and local land use practices and erosion pattern. So, that is as far as erosion pattern is also concerned, that is very important. Now, surface detention is the water detained or water temporarily detained on the surface. So, this is one of the necessary requirement for surface runoff to occur. So, this is actually somewhat when we consider hydraulic modeling, it can be part of surface runoff itself. So, some of the controlling factors are surface micro relief, vegetation, surface slope, topography and rainfall excess. So, depending upon whether we are going for very accurate way of hydraulic modeling, we can consider the surface retention or detention. Actually, it is very complex, very complicated to identify how much will be the retention or detention. So, generally maybe a small percentage of the rainfall can be considered as surface retention or detention. And then the next important, very important hydrologic process is so called infiltration. So, actually that is one of the most important hydraulic process which decides how much will be the from when we consider precipitation to runoff, how much will be the water loss. Actually, it is not a loss, it is going to the earth or through the soil to the aquifer system. So, this infiltration now we will discuss in detail. So, infiltration is the process by which water on the ground surface enters the soil. So, infiltration capacity of soil determines like amount and time of distribution of rainfall excess for runoff from a given storm. So, you can see that now rainfall taking place, and then the say what is happening here, the rainfall taking place, this is a soil condition. Now, through the soil pores, the water will be infiltrating down to the soil. So, this is unsaturated layer, and then it slowly goes to the capillary fringe and finally to the groundwater. So, this is very important. Infiltration is concerned very important for estimation of surface runoff and also subsurface flow and storage of water within a watershed. So, how much is subsurface storage, this is all decided by the infiltration. So, some of the important controlling factors as far as the infiltration is concerned like a soil type, like a size of particles, then degree of aggregation between the particles, arrangement of particles, then what kind of soil it is, clay soil, sandy soil, then vegetative cover. So, whether it is the vegetation cover is sand, say grass, or say what kind of vegetation cover is there, either a forested or non-forested. Then surface crusting, then season of the year, and then some of the other controlling factors like antecedent moisture, what is the moisture holding of the soil, then rainfall hydrograph, what is the excess rainfall. So, this rainfall is whether if it is continuously taking place, then the infiltration will be keep on reducing, then subsurface moisture conditions, etc. So, there are so many controlling factors. Actually, this infiltration process is very difficult to quantify, since the soil nature is very complex, and then it is not so easy to identify. But anyway, a number of methodologies have been developed by various researchers in the last few decades, and so using either one of these methodology suitable to particular area, we can identify how much is the infiltration losses. So, next one is the infiltration estimation. So, infiltration measured, say we can measure for the given location, we can use infiltrometer. So, this is so called double ring infiltrometer. So, we can do experiment for the particular location and then identify how much is the infiltration rate. And then rainfall runoff plots, say particular plot is concerned, we can say small plot we can consider, and then how much is the, so if you identify how much is the evaporation losses, then say how much is the runoff, from that we can identify how much is the infiltration taking place. Then entry of water into soil surface measured on a small plot of soil, and then that gives the infiltration rate. So, infiltration rate generally we put as volume per unit of time per unit of area, or depth per unit time. So, this shows taking from Ghanshyam Das. So, with respect to time, infiltration rate is given here. So, it can be say like mm per hour. So, it depends upon the soil like sand, then loam, then clay. So, it is drastically varying. So, as I mentioned, number of methods are available to estimate the infiltration. So, some of the important methods include Horton's equation, Green-Samt equation, Phillips equation, Darcy's equation, soil conservation service curve number equation, Horton equation, Kostiakov equation, like that. So, number of equations are available in literature to identify the infiltration estimation. So, depending upon the data availability for the particular location, depending upon the accuracy which we are looking for, and then data availability, we can choose particular infiltration estimation method, and then we can calculate the infiltration. So, here we will discuss 2-3 important methods. Say one of the commonly used method is called Horton equation. Here the assumption is that infiltration starts at a constant rate f0 and is decreasing exponentially with the time t. So, the equation is Ft is equal to Fc plus F0 minus Fc into e to the power minus kT, where Ft is the infiltration rate at time t, Fc is the initial infiltration rate or maximum infiltration rate, F0 is the constant or equilibrium infiltration rate after the soil has been saturated, or minimum infiltration rate. Then K is so called a decay constant specific to the particular soil. So, this equation we can utilize, Horton equation. Then another commonly used equation is called the Phillips infiltration model. So, the equation is F is equal to half SI into T to the power minus half plus K. So, where SI is the infiltration sorptivity, K is hydraulic conductivity, which is considered equal to saturated hydraulic conductivity Ks, and T is the time. So, say Phillips infiltration model is also another commonly used infiltration model, and then another infiltration equation is so called a Horton equation. So, here the equation is F is equal to G I A into S to the power 1.4 plus F C, where F is in inches per hour, G I is a crop growth index that ranges from 0 to 0.1 to 1. A is the macro pores associated with the plant roots, Fc is the steady state infiltration rate, and Si is the available storage in the surface layers. So, like this various equations are available. So, depending upon the data availability and depending upon the soil nature and other conditions, we can choose a particular equation to estimate the infiltration. So, if we are not going for very complex equations like Horton or any of this equation, we can use say we can say consider certain percentage of the rainfall is going as infiltration. So, we can describe it in terms of infiltration index for determination of loss of rainwater due to abstraction. So, this method assumes constant value of infiltration capacity for the full duration of storm like phi index. So, we can consider average abstraction of rainfall like 10%, 20% or 30% like that. So, phi index, and another index is called the W index. So, this considers initial abstraction, and then very difficult to determine the correct values of initial abstraction. So, so commonly say this phi index, we can simply say that this much percentage of the precipitation is going as phi index. So, but if sufficient data is available and if we are looking for a accurate measurement of the infiltration, then we have to use various models like Phillips model or Horton equation or Horton's empirical infiltration equation like that. So, this is about the estimation of the infiltration. So, as I mentioned, infiltration is one of the most important hydrologic process which we have to consider, and the precipitation to runoff depends upon the how much is the percentage of the infiltration taking place at the considered location. So, now we will discuss some of the other important hydrologic processes. So, now next one is the evaporation. So, as I mentioned, there is always say when the rainfall is taking place continuously, the evaporation loss may be less, but otherwise evaporation is taking place from all the surface water bodies or from the soil, or as transpiration and evaporation from the plants. So, all this taking place. So, evaporation is another important hydrologic process which we have to consider. So, evaporation is the process where liquid water is transformed into a gaseous state at a temperature less than the boiling point through the process of transfer of heat energy. So, evaporation of water occurs when the surface of the liquid is exposed, then allowing molecules to escape and form the water vapor. So, this vapor can then rise up and form the clouds. So, you can see that evaporation from the water surface taking place, and then cloud formation taking place, and then that is a part of the hydrologic cycle. Then the important factors affecting evaporations here I have listed, like solar radiation, differences in vapor pressure between water surface and overlying air, then relative humidity, temperature, winds, atmospheric pressure, etc. So, there are number of factors affecting the evaporation. So, some of the important factors I have listed. So, now when we are looking for water resource assessment as far as a watershed is concerned, say we have to identify how much is the evaporation losses from the say for example from the lakes, from the reservoirs, or from the river, or any other water body, and then of course the various other losses from the soil, etc. So, now the exact measurement of evaporation is very difficult. So, generally say for large water bodies we can consider some experiments, or we can use some equations which are already developed. So, from open water surfaces we can measure the evaporation using various equipments like atmometers, then evaporimeters, or open pans. So, this shows a typical pan. So, this photo is taken from this website. So, from this say we can fill this pan, and then according to the various say with respect to time how the variation in depth taking place. So, accordingly we can identify how much is the evaporation loss. So, evaporation pans are concerned, so that gives the evaporation using the water filled in containers like this. So, we can observe how much water is lost over time. So, different types of pans are available, like US class A pan, ISI standard pan, Colorado sunken pan, Russian GGA pan, So like that. So we can identify a coefficient called pan coefficient, which is the ratio, say for example, lake to pan evaporation. So we can identify the coefficient and then multiply to identify how much is the evaporation is taking place for the given water body or given reservoir or the lake which we consider. So other than this experimental measurements, we can also estimate using various equations or various methodologies listed here, like water budget method. So this from ponded water or lakes reservoirs, we can identify, we can account all the inflows and outflows, and then we can identify how much is the evaporation. Then energy budget method. So based on application of law of conservation of energy, so we can identify the say how much energy is taken for evaporation, and from that we can calculate the evaporation. Then mass transfer, so called aerodynamic methods. So this is based on turbulent transfer of water vapor from an evaporating surface to the atmosphere. So a number of mass transfer models are available in literature. Then a combination of this, like mass transfer and energy budget methods. So then also number of empirical formulas are used for evaporation estimation, like USGS and USBR formula, where evaporation is equal to 4.57 T plus 43.3, where E is the evaporation in centimeter per year, T is the mean annual temperature in degree centigrade, like that. So say we can identify, so as I mentioned, evaporation pans also we can utilize. So evaporation is a major loss as far as the surface water reservoirs are concerned. So it is always say depending upon the area, like humidropic areas, it can go to 30%, 40% or even up to 50% of evaporation losses, say from the reservoirs or the lakes. So if we can control the evaporation by using various measures, so that we can reduce the evaporation and then we can have better use of the available water. So here I have listed various evaporation control measures, like storing water in covered reservoirs, then making increased use of underground storage, then controlling aquatic growths, and then building storage reservoirs with minimal surface areas, then conveying in closed conduits rather than open channels, then applying a thin chemical or monocular film, like by using cetyl alcohol, and then that reduce evaporation, say about 20 to 50% by preventing the water molecules to escape from the water surface. So actually this we can only thing is that it is slightly expensive, but no water quality effect, like it is colorless, odorless and non-toxic. So even we can use this chemical film also to control the evaporation. So if we can reduce the evaporation, then the water stored in lakes or reservoirs we can use for dry periods. Then another important hydrologic process is the transpiration. So the transpiration is the vaporization of the liquid water contained in the plant tissues and the vapor removal to the atmosphere. So since say most of the land surface is covered by the vegetation, then the accordingly the transpiration varies. So the crops predominantly lose their water through stomata. You can see that this is typical the cell structure within the leaf. So this is so called stomata. Then these are small openings, as you can see here, say small openings on the plant leaf through which gases and water vapor pass. So nearly all water taken up is lost by transpiration, and only a tiny fraction is used within the plant. So plant takes a lot of water through its roots, and then the photosynthesis taking place, and then so much of water vapor will be lost as transpiration through the stomata. So transpiration depends on the energy supply, vapor pressure gradient and wind, soil water content, and the ability of the soil to conduct water to the roots, crop characteristics, environmental aspects and cultivation practices. So actually most of this transpiration will be taking place during the daytime. So 95% of daily transpiration occurs during the daylight hours. So, now say most of the time it is very difficult to separate this transpiration and evaporation. So, that is why we will be using a term called evapotranspiration. So, soil moisture lies between the limits of wilting point and field capacity, so that there is no effect on transpiration. Now, say transpiration is concerned, we can there is a certain equipment called phytometer, which we can use to measure the transpiration for the given plant is concerned. So, as I mentioned, it is very difficult to separate evaporation and transpiration. So, we use the term called evapotranspiration. So, evaporation and transpiration occur simultaneously, and there is no easy way of distinguishing between the two processes. So, say as far as the plant is concerned, water is taken through the root, and then say some water is going as evaporation also, and then transpiration also. So, some of the important definition as far as evapotranspiration is concerned. First one is potential evapotranspiration, PET. So, this is the rate at which water, if available, would be removed from the wet soil and plant surface and expressed as the latent heat transfer per unit area or its equivalent depth of water per unit area. And then this PET is the measure of ability of atmosphere to remove water from this surface through process of evaporation and transpiration, assuming no control on the water supply. Then another important definition is so called actual evapotranspiration. Then this is a quantity of water actually removed from a surface due to the process of evaporation and transpiration. So, now we can also estimate the evapotranspiration using various equations. So, like the crop water need is actually potential evaporation minus actual evapotranspiration, and we can put a coefficient called crop coefficient, which is the ratio of actual evapotranspiration to potential evapotranspiration. So, there are various theoretical methods like Blaney, Criddle, Penman, Mondolit methods. Then empirical methods like Thornwright method, then field methods like lysimeter, and then field plots, soil moisture depletion studies, etc. So, also we can use analytical methods like energy or water budget methods like evaporation. So, here also we can use the analytical method as far as the estimation of evapotranspiration is concerned. So, for example, one of the commonly used method is so called Blaney-Criddle method. So, here the assumption is consumptive use of water by crops is related to mean monthly temperature and daylight hours. So, this provides a rough estimate. So, for extreme climate condition, method is inaccurate. So, this depends upon whether the windy, dry or sunny areas. So, here the reference crop evapotranspiration is obtained by P into 0.46 T mean plus 8, where P is the mean daily percentage of annual daytime hours as far as the particular location is concerned, and T mean is the mean daily temperature. So, this equation we can utilize depending upon the area. This P can be identified, and once the temperature is known, we can identify how much is the evapotranspiration for the given location. So, now after all these losses, then next step is the surface runoff taking place. So, surface runoff actually is the part of precipitation which during and immediately after a storm event appears as flowing water in the drainage network of a watershed. So, this results from the direct movement of water over the surface of watershed, precipitation, excess of abstraction, demand or emergence of soil water into waterways. So, the surface runoff generally occurs when the rate of precipitation exceeds the rate of infiltration. So, that is one of the essential condition. So, there are number of factors, controlling factors which decides the surface runoff, like climatic factors like precipitation, intensity, duration, aerial distribution and storm pattern, then evaporation and evapotranspiration. Then some of the physiographic factors like watershed characteristics, size, shape, land use, infiltration rate, slope, etc. Then channel characteristics like size, cross section, slope, roughness of channel bed, and then the drainage pattern and density of the drainage of the area which we consider. So, then as far as the surface runoff is concerned, so we can classify into overland runoff and then channel flow, overland flow and channel flow. You can see that what is happening within the watershed. So, if rainfall exceeds the soil infiltration capacity, water fills surface depression, then water spills over say downslope as overland flow and eventually to the stream or the channel that is so called channel flow. So, surface runoff generated either by rainfall or by the melting of snow or glaciers. So, we can measure like say as far as the runoff is concerned in a channel, we can measure using say like say H flume or various automatic water stage recorder we can use to measure the runoff, what is happening within the outlet of a watershed or a particular location of the stream or the river is concerned. Then if we consider the various runoff mechanism, then the runoff say from precipitation runoff takes place when infiltration excess or so called excess overland flow. So, this is so called Hortonian or unsaturated overland flow. So, this occurs when rate of rainfall on a surface exceeds rate at which water can infiltrate the ground and any depression storage has already been filled. So, that is so called Hortonian or unsaturated overland flow. Then second mechanism is saturation excess overland flow. So, when soil is saturated and depression storage fill, rain continues to fall, rainfall will immediately produce some surface runoff. So, that is so called saturation excess overland flow. Then say this depends, the runoff depends upon the antecedent soil moisture condition. So, soil retain a degree of moisture after rainfall. So, the residual water moisture affects the soil infiltration capacity. So, depending upon the antecedent soil moisture, then when the next rainfall takes place, so whether the faster runoff or slow runoff taking place. Then finally, the subsurface return flow. So, that is so called a through flow. So, after water infiltrates the soil on a upslope portion of a hill, water may flow laterally through the soil. So called exfiltration. So, flow out of the soil. So, this is close to a channel. So, finally, this will be also the part of runoff. So, various surface runoff mechanisms are there as far as the precipitation to runoff is concerned. So, finally, the steps to hydrologic modeling. So, what we can do, we can delineate the watershed, then we can identify the various hydrologic processes. So, we can obtain the hydrologic and geographic data, then select various modeling approaches as far as various hydrologic processes are concerned, and then we can estimate the various quantities. Then we may go for calibration, verification, and then we can use the particular models for the assessment or prediction as far as precipitation to runoff is concerned. So, we can use models. We will be discussing about these various models in the next lecture. So, the model is concerned, we have to assess what happens if land use and land cover is changed. So, that we have to assess. Then we can go for a prediction mode, say for the given rainfall condition, how the flooding can take place. Then we can go for design also, how much flow will in a 10-year storm or 5-year storm can take place. So, before closing these lectures, we say here two example problems. So, first one is use of Thesian method to identify the average rainfall. So, here this figure you can see that 5 rain gauge station, the observed rainfalls are given here. Then the polygon area we can identify as we discussed. Then we can identify the rainfall volume. So, we can calculate the average rainfall by considering the total volume, and then we can, so total volume is obtained for station A, the rainfall multiplied by the polygon area. So, that will give the volume. So, then we can sum it up, and then we can divide by area, that gives the weighted average annual rainfall, not average for the storm concerned, weighted average rainfall for that particular storm which we consider. So, that is the way use of Thesian polygon method. Then to calculate the evapotranspiration, say if we want to use Blaney-Criddle method. So, say for example, temperature is given as 27.5 and 19.5 the maximum and mean for April. Then we can use this Blaney-Criddle equation. Then from the given latitude we can identify the p value as 0.29, and then we can calculate the evapotranspiration, so reference crop evapotranspiration by using this equation. So, this shows how we can use the Blaney-Criddle method. So, these are some of the important references used for today's lecture based upon these say books and websites. Then before closing the lecture, say one tutorial question, what are the different types of abstraction losses associated with rainfall for the development of watershed management plans? What are the important abstraction losses to be considered? So, for the typical watershed, we can say tropic, semi-arid or arid regions, identify the significance of each losses, then illustrate various methodologies used to quantify them. Then few self-evaluation questions like illustrate various hydrological processes within the context of hydrological cycle. Then describe different types of rain gauges, compare the Theisian isohydral method for computing average rainfall and bring out the basic differences and advantages. Then discuss different methods of evapotranspiration estimation, and a few assignment questions like describe important precipitation mechanisms, discuss the importance of rainfall intensity, duration and frequency in runoff generation. Then describe various methods of estimation of infiltration, then illustrate surface runoff and mechanisms of generation of surface runoff. So, all these related questions today's lecture we have discussed the details. So, once you go through the lecture you can answer all these questions. So, now one unsolved problem, say for your watershed area, obtain the rainfall data for the nearby rain gauge stations for few storms, and using various methods like arithmetic mean, Theisian mean method, isohydral method, you can compute the average rainfall by all methods and compare. So, we can identify say each the advantages and limitations of each method. So, once you get the rainfall data, you can draw isohyds for the given area and construct the Theisian polygon as we discussed earlier. Then we can compute the average rainfall for the given storm conditions. So, now based today what we have discussed is the various hydrologic processes. Now, we have seen various equations for our various how to estimate the various processes. Now, based upon this, now in the next lecture we will discuss the hydrologic modeling as far as the precipitation to runoff. So, we will discuss in detail the various models and then how we can go for watershed modeling based upon these models. Thank you very much.